Good morning, everyone. In my talk, I'm actually going to build on what Inma just told you. I'm just going to continue that story. We're at a very interesting stage in the history of humanity. Many of the things that we heard about when we were young, very young, science fiction, is all happening right now. The world is really changing. And I think one of the main messages that I want to bring to you today is really this realization that space technology, space exploration is not something out there, but that it's really an inherent part of our current state of humanity, and it's there to stay. And there's a lot of opportunity for all of us to join that. The time when space exploration was only for aerospace engineers is over. It's really something that all of us are involved in and can be involved in. And these are just some additional examples that illustrate what is really going on today. On the top left, you can see an example of 3D printed space architecture, something that we also saw in the previous talk. But this one is quite peculiar. It's an ice house. It's actually an architecture that is printed instead of using regular 3D printing material, using water and creating an ice shell around the architecture. Now, you might wonder, why would you use ice to build? Well, first of all, it's in a location in Mars. I mean, this is a study. It's not been done yet. This is in a location in Mars where the temperature is always below zero, obviously. Otherwise, your house would melt. But the thing is, out there in space, one of the big challenges is radiation. And water really protects you very well from radiation. So creating that ice house is a really interesting solution to deal with that challenge. On the right top, you can see a spacecraft that probably all of you have heard about multiple times, which is the Starship concept developed by SpaceX. And this is quite a peculiar approach to space exploration. It's really a paradigm shift. It's a massive rocket. It's planned to be able to move large amounts of equipment and people into space as never seen before, really a magnitude of difference. And I think what is interesting here as well, on top of the fact that the capacity of the spaceship is really much improved, is the sustainability element here. It is supposed to become a really fully reusable rocket, and that's something we really need to evolve to. On the lower left, you can see one of the many examples of American commercial space stations that are in development right now. So in a couple of years, we'll have a range of space stations circling Earth for commercial activities, business research, industrial research, scientific research, space tourism, all blended into one. And then the image on the right, on the lower right corner, is basically an artist's impression of a plan of China to build the largest spacecraft ever. It's a study, they're still studying it, but the goal is to create a space infrastructure that is at least 1 or even more kilometers long. And that's the kind of things that are happening right now. Like I said, all this used to be science fiction, but it's happening. Now, this new domain, relatively new, because it's already going on for a while, this new economic domain is called New Space, as you could also hear about in the previous talk. And New Space is really this opening up of space exploration for people, for all of us, for companies. And the essence here is that instead of space being something very difficult to get into and very long-term and extremely expensive, things have become more, how to put it, more manageable, smaller. You can now launch a very small satellite and actually get really significant data out of that. That was 20 years ago, for example. That would have been much more difficult. But it's not just the miniaturization. Also, the access to space has much improved. That's because the costs of launch have lowered. There are all kinds of companies that provide you with access to the International Space Station, for example, where you can run an experiment and immediately get real-time access on your own laptop with your experiment on board of the International Space Station. That was, like I said, 20 years ago, that was almost unimaginable. So there's a lot has changed, and there's a lot of possibility. So it's really within that evolution that, of course, this question comes up a lot. And I get that question a lot. Why focus on space? Why talk about space when so much is going wrong on Earth? I don't need to give you a list on all the things that are going wrong on Earth, politically, socially, and ecologically especially. There is a big contrast, right, between, for many people, between investing in space and then climate change, for example. People are like, shouldn't we fix Earth before we go out into space and mess up that world? There's a few answers to this difficult question. Well, first of all, the classic answer to this question is this one. Space always has been providing us with new innovations and new materials that actually benefit life on Earth. And it's a good argument, but it's not enough, I think. Here are some examples of the things that really came out of the world of space exploration, have changed our daily lives. We're talking about cordless tools. They were basically invented for space, water filters, lenses that cannot get scratched, freeze-dried food, etc. So there's all kinds of very particular examples of technologies that we're using today that we don't even realize that actually they come out of space. But it's a bit deeper than that, and especially when we're talking about climate change. Actually, what people sometimes forget when they criticize space and they're like, we should fix Earth first, we should deal with climate change is first. Climate change was actually discovered because of space exploration. It's because of the network of satellites and the constant monitoring and all space science that we discovered and started to understand climate change. And it's also going to be the only way in which we're going to be able to manage climate change. So it's really intertwined. And I think this is really key here, that we cannot look at space and space exploration as something separate any longer. We really have to look at something that is really a part of human civilization. It's almost like our culture, our civilization, has now stretched from the surface of Earth, or even the depths of the seas, all the way into space. And it's this one, you have to look at it as a unity, as just one area of activity, of creative activity, and of economic activity and scientific activity. So what I'm going to talk about today is two topics that I'm personally working on. One is space farming. Yes, we can farm in space, and we need to farm in space. And the second one is bio-inspired engineering. To keep a human alive, a human body alive, these are the figures. These are your daily metabolic needs. You need a certain amount of oxygen, a certain amount of calories for food, and a minimum amount of water to just keep a human body functioning anywhere, also in space, of course. Now, the problem is, if you start thinking about deep space missions, like, for example, going to Mars, and you would basically want to take everything that you need with you without recycling anything, you will need a lot of mass. This is a very unsustainable approach to go to space. So this is absolutely not a way to go about it, to just take everything you need at the start of your mission and then waste everything. So when you want to settle on Mars or you want to settle on the moon, you'll have to build some sort of recycling systems. Now, some of those recycling systems already exist. In the International Space Station, for example, there is a very elaborate water recycling system that is operational. Now, we need to push things further when we're talking about settlements further away from Earth than the International Space Station. And what better solution to use than nature? Nature is a master in recycling and reusing. So why not use that? And this is something that the European Space Agency has actually been working on for quite some time. The system that they developed is called Melissa. And Melissa is an artificial regenerative ecosystem that basically recycles all human waste and then turns it back into nutrients for plants that provide oxygen and food for the astronauts. And the conceptualization of this ecosystem is as follows. You basically have 5 compartments. Humans are one of the 5 compartments. And all waste products from humans, and we're talking about everything, toilet waste, urine, sweat, CO2, everything is being captured, and then using a series of 3 different types of bioreactors inhabited by different types of microorganisms, these big molecules are gradually broken down, turned into nitrates and CO2 that then can be used by plants and edible algae to provide fresh food, fresh oxygen, and also purify the water, which is a fantastic solution, right? But it's not a solution that is just applicable in space. this would also be a very interesting approach on Earth. I think you would all agree with that. And so we enter a domain that I call molecular sustainability. It's this idea that resources are waste is actually very useful, as we all know, but developing the sensitivity that we look at waste as molecules that are actually valuable, each one individually. Taking a molecule, breaking it apart, and reconfiguring it into something useful. It's a very radical approach to sustainability, way beyond a lot of the sustainability programs that we already have running. And I think it's that mindset, that sensibility, that is what we need on Earth. Now, this story, what I just told you, is a massive contrast with the reality of, for example, food waste. These are some of the figures. 2.5 billion tons of food waste are produced each year, and in the end, about almost 40% of food production is wasted. What an immense contrast, right? I mean, it's always going to be, it's probably impossible to completely eradicate food waste. I mean, we all throw away something every now and then. There's nothing wrong with that, but 40%? In contrast with that molecular sustainability dream we have in space, you see this mismatch between what's happening on Earth and what is actually being investigated in space, and how this could be, brought together. I think there is a lot of opportunity there. This is an interesting graph that I got from a report from the Ellen MacArthur Foundation, who's really focusing on this problem of the need for a circular approach in terms of waste. And it really indicates that, for example, cities produce so much waste, and there's so much value in that waste that is completely ignored, and we really need to change our thinking about this. So I've been talking so far about what we can learn from space and how we can apply it back on Earth, how we can apply technologies, certain sensitivities back on Earth, and how it could also improve life on Earth. But the story goes both ways, and that's quite interesting. I kind of bumped into that in this research project that I did, which was a program in the Netherlands in which I brought together people from the horticulture sector, growing food, and people from the space sector. And the idea was to make them communicate, just make them meet and see if there's any opportunities for them to collaborate. And of course, there are many innovations from space that could be useful on Earth, technological innovations in terms of water purification technology, sensor technology, robotics, etc. But we also discovered that actually, if we want to go into space and we want to continue exploring space and expanding humanity in space, we need the tacit knowledge of these growers. It's not enough to grow a lettuce in space and do some scientific studies on the lettuce. We really need to grow large quantities of food in space if we want to sustain people in space. We need to grow calories in space. And for that, it's not enough to look at scientists. We need people that actually know how to grow large amount of food on Earth. So they can really help out working with people in space. And I really love that, because essentially, one of the things that I am is a connector. I love to connect worlds. And this is one of those examples where both worlds could really benefit from each other. Now, biology, basically this is what I do. I bring biology into space. And what I just talked about is one example. It's developing this ecosystem approach for space, and then also learning about this for Earth. Now, bio-inspired engineering is another way in which we can use biology in deep space. My current field of research is actually interstellar exploration. I'm doing theoretical research on how humanity could move beyond the solar system and start exploring nearby stars. At this point, we don't have the capacities yet, but technically this is feasible. Now, there's something very peculiar, very characteristic about trying to explore interstellar space. You're dealing with deep uncertainty. If you're going interstellar, it's very different than going to the moon. In the Apollo program, remember, it was Apollo 11 that was the first one to touch the surface of the moon. Why was that? That's because the previous Apollo missions were missions that were meant to go close to the moon, but each time come back to Earth. So each subsequent mission would go a little closer to the moon, then it would go back to Earth, then they would optimize the spacecraft and the mission using the lessons learned from that mission. And so gradually, incrementally, they would get closer and closer to the moon until they were ready, the 11th mission, to actually touch down. If you're going interstellar for these deep missions, that's not an approach that would work very well. Going interstellar and then going all the way back to Earth to fix a few things and then going back interstellar, that would take centuries to get anywhere. So that's not really a very smart option here. But that's really a conundrum, right? You're dealing with an uncertain challenge, with a challenge full of uncertainties, and you're asking engineers and scientists and entrepreneurs to come up with solutions for that. How would you do that? Well, that's where biology comes in. Why not develop a concept for a growing and evolving spacecraft that can actually respond to unexpected challenges? And this is the goal of our research. It's really trying to come up with a new paradigm on developing spacecraft. Now, I'm not doing this alone. When I'm standing here and I'm talking about my research, I'm always representing a large team that I'm working with. And it's really crucial for everything that I do. Bringing together all these disciplines, making them work together, and only in this way, really, we can move forward and we can really tackle these big challenges. Now, the concept that we come up with is the following. We're basically combining two technologies that are currently in development. On one hand, asteroid mining, and on the other hand, 3D manufacturing in space. There are millions of asteroids out there in the solar system. They contain a lot of valuable materials. Materials that are useful on Earth, but materials that are also very useful in space. They're actually resources that we can use in space in an in situ resource utilization approach that Inma also introduced before me here. And so using that as a resource to build your spacecraft in space is one part of the concept here. The second one is that instead of building components of your spacecraft on Earth, we might as well start building in space itself. And that's where 3D printing, 3D manufacturing could come as a solution. And what you see here is an example of such a potential 3D printing robot. And so the concept we're proposing in our theoretical research is transforming an asteroid into a spaceship. It's hollowing out a spaceship using robotics, using those materials subsequently to 3D print an architecture inside of the asteroid and then extending from the asteroid. And the idea is that on top of the usefulness of the asteroid as a resource, it also doubles up as a shield against incoming impacts. And since the asteroid already has a certain velocity, by reorienting the path of the asteroid, your craft can be moved to a different target. And so this is really a very different approach, but at the same time, it's something that actually comes out of science fiction. I'm sure there are science fiction fans in the room here, and there are novels that talk about transformed asteroids. There are computer games in which you have this. So there's quite a bit of exploration and fiction there. But the difference is here, we are turning it into science. We're turning this into a scientific study, turning this into a computer simulation in which we can investigate the behavior of such a spacecraft. Now, when I'm talking about this, I'm actually talking about the domain, the relatively new domain of morphogenetic engineering. And in morphogenetic engineering, you're basically using a bottom-up approach to engineering. And the best way to explain it is using termites. Termites live in termite colonies, as we all know, with these typical termite mounds. But the actual mounds that we know are the cooling towers of the colony. The actual colony is underground. It's a farm. Termites are farmers. They farm fungi. So the larvae and the termites and the fungi all live underground. They need oxygen. So the challenge for termites is, how do we bring in fresh oxygen while keeping out the heat? Because termites mostly live in tropical environments. And through evolution, termites actually discovered a way how to tackle this problem. They basically have a very interesting approach to building that cooling tower in terms of orientation towards the sun, the morphology of the cooling shafts, etc. The crucial thing here is that when termites decide to build a new termite mound, you don't have one master termite running around with the master plan telling every single termite what needs to be done. There is no plan. And still, they find incredibly well-crafted solutions. How does that work? Well, it works through emergence. Individual termites have particular rules in which they interact with each other and with the environment, and it's strictly through those rules and those interactions that the solution emerges. It's like a swarm of birds. When you look at a swarm of birds in the sky, sometimes it looks like an incredible mathematical structure. Nobody designed that swarm. The swarm of birds emerges out of the birds using 3 rules in which they interact with each other. And so that's really a very powerful paradigm to design solutions for the future. Now, I've been talking about a growing spacecraft. One other element, we basically have 3 biologically inspired elements in our concept. The second one here is to embed the idea that the technology that is building your solution can also self-replicate. So that's the second component that we're basically adding to our concept. And once again, this is nothing new. John von Neumann was the famous mathematician that actually started building a whole mathematical theory on self-replication, self-replicating automata. And even NASA in the 80s started investigating the possibilities of machines that would replicate themselves using local resources. But then nothing much was done with that. We've picked up that idea and are using that in our concept. And then the third concept is dealing with this uncertainty. What is this uncertainty in deep space? Well, we're talking about radiation, constant cosmic radiation. We don't really know the long-term impacts of this radiation on an ecosystem, on humans, on technology. Secondly, space is not vacuum. There are actually particles in space. So when your spacecraft travels with a very high velocity for interstellar exploration, even these small particles can cause a lot of damage. So how do we deal with that? Well, we're basically embedding evolution into our spacecraft. Spacecraft is built, the architecture is built out of modules, and the modules can be reconfigured. And so in this way, the shape of the spacecraft can be adjusted according to the challenges that the spacecraft senses are coming up. And it's using evolutionary algorithms to find a new optimal shape of itself. So that's a third biologically inspired element that we've been using in aerospace engineering basically. So we're talking about growth, replication, and evolution, typical concepts from biology that suddenly found an application here. So, conclusion. I think what I really want to, I think my most important message here is, first of all, space is here to stay. It's really an interconnected part of our current society, and there's a lot of opportunities there, of course. And the thing is, we have to look at it as a mutually beneficial understanding. It's not that we have to help space, but space, of course, also helps Earth. But yeah, that's what I wanted to say. It's basically mutually beneficial. Of course, there's all these interesting innovations coming from space to Earth, but we can also help to develop space. And then secondly, for developing solutions for all these complex problems, we can use something that has been evolving on Earth for a very long time, and that is really nature, with all its beautiful solutions that have been evolving over so many years, really tackling and then using that in engineering. Thank you so much.
Thank you so much, Angelo. Please don't run away from me. I hope, guys, you enjoyed this. I do have a question for you, I know you're also a photographer and an artist, and I was about to ask you about the black hole. We now have the photographs in our Milky Way, but I'm not going to ask you that, because when I was listening to your presentation, it really got my blood like rushing through my veins when you were talking about the agriculture and biology, and what was coming through my mind was the Martian, growing potatoes, and then bingo, I saw the photo from the movie. But Ridley Scott also has another movie, right? The older one, The Alien. Biology, space, one may claim that many things can go wrong, and I assume you do get this question time to time. So, Angelo, what are your maybe main frustrations? What are those fears and misconceptions which people address your way when they talk about your work at the intersection of biology and space? How do you debunk them? How do you manage those fears of humanity, of something going wrong?
Well, I basically already answered part of your question, of course, during my talk. One of the biggest questions that often comes up is, why space? There's so much to do on Earth, and I think I addressed that in my talk. And really, I think when people start to see that there is communication possible in both ways, and you can actually be part of it, it's not something that is far away from you, and your taxpayer money is used for things that you'll never, have any connection with, but you can actually be part of it. You can set up your own company, you can set up your own research, you can set up your own outreach program together with space agencies. I know European Space Agency is very open to this. I think that really changes the dialogue. And I think one of the things that we need to relearn or learn over and over again is really looking at things, two things. Looking at things from a complex systems perspective, not just one topic, but really looking at topics as part of a bigger conversation and a bigger whole. That's why I usually take a step back and I look at human civilization and the history of human civilization. So that's the second thing. We need to learn to think more in deep time and look at this bigger perspective instead of only looking at short-term solutions and short-term processes. So I think if we can sharpen that sensitivity on one hand for complex systems and what complex systems are, and that our world is a complex system, which doesn't mean that we cannot understand it. It's just a lens through which we can understand it. And then secondly, if we start to look at things a bit in a bigger perspective, I think that really helps to understand what's going on and find your own place in that process.
Right. Thank you so much, Angelo. Thank you. I do think that we had two amazing keynotes complementing each other. So thank you so much.
You're welcome.
Yes, a round of applause to Angelo.